Hello, everyone. So hopefully people are doing well today, and hopefully people can hear me okay, and we will get started in just a minute then here. I want to take a second here at the beginning to highlight all of our kind of chat rules again, right? So please keep the chat relevant to solving math questions, especially once we start doing some of the concepts and doing some of the math problems that way as well, right? Be nice to each other, no insulting or kind of talking too mean to each other. Right? Sharing answers, but don't repeatedly share over and over and over. And I will do my best to kind of delete comments that are inappropriate and time people out that way as well. So please do not make me kind of do something like that either. So yeah, a little bit, right? We're still kind of exploring some different options kind of later on that way in terms of other kind of planning and stuff like that as well. And then we'll kind of go from that kind of later on as well. Okay, so let's kind of get started then. Maybe we're going to do some problems, right? Geometry problems, middle school kind of level. Maybe some of these will be review questions. I do want to do a couple kind of concepts as well. And so first kind of warm-up question we have here is about kind of 7 congruent rectangles are kind of arranged in this figure below, right? So we have kind of these 7 shapes. They're all congruent. They're all the same, right? We know that the perimeter of the small rectangle is 36, and we want to find the perimeter of the big rectangle here. Yeah, so we're starting out with a warm-up question, right? Not all of our questions are kind of too difficult here necessarily, but we want to kind of figure out the answer here. Okay, so a lot of people are saying kind of 72 in this case. So there's lots of different ways to go about solving this. You can actually kind of think about that little kind of perimeter there as well. Now, let me kind of do a nice little kind of argument here. So if we have the length and the width here, I'm not going to really solve an equation in this case, but if we have the small rectangle has length L and perimeter and width W, we know that 2L plus 2W equals 36. In terms of L and W, what is the perimeter of the entire rectangle, right? Well, we could start labeling sides here, right? L, W, etc. And what we can pretty easily note here is that, right, the big rectangle has perimeter, right, 4L plus 4W, right, which is double the perimeter of the small one. We can kind of notice there is equal to 2 times 36 equals 72. So that kind of is the answer that most of you guys are kind of sharing there as well. But I just want to kind of wanted to show quickly as well that you can do this without actually finding the kind of length and width in that way too, right? But it is good to kind of recognize here we're just ending up doubling that rectangle there. Okay. Yeah, you can solve for L and W, of course, but that's kind of the general strategy here. Okay. So solving a geometry question, we did this in the morning if you were here, but just kind of reviewing some stuff. Read it carefully, draw and label a diagram if needed. Will extra lines or extra breaking up of the diagram be kind of helpful there too? And so kind of going from there too, right? What else do we maybe need to know to kind of solve the kind of problem from there too? Okay, so what are some kind of concepts and things for geometry problems that we need to kind of talk about, or at least know we have to review, right? Areas, perimeters, volumes, all of these things should be kind of pretty straightforward and things you should know, right? Triangles, quadrilaterals, squares, right? Rectangles, parallelograms, trapezoids, different shapes with more sides, right? 6-sided hexagons, 8-sided octagons. And then if we kind of start talking about 3D shapes, right? Of course, these last lines are all of our kind of 3D shapes there, right? Knowing at least some basics, even if we might not do too much of that right today, right? These are our kind of basic shapes in 3 dimensions as well, right? So kind of prisms are like boxes, or you could have a triangular prism, things like that as well, right? Then pyramids all go to the one point on top. Spheres and cylinders are the curved ones, stuff like that as well. So one very, very important, still basic theorem, right? Even in middle school geometry, you should know this, right? Pythagorean theorem. So in a right triangle with an angle of 90 degrees, a squared plus b squared equals c squared is, right, only if we have a right triangle here. So here kind of would be our diagram. We have our sides here, C, A, B. We have our lengths, a squared, b squared, and our ABC, and things like that as well. Yeah, so depending on your age, you may or may not have seen this, right? You might have learned this kind of either earlier as well. But, right, this kind of is a very important theorem this way, too. Remember here, if and only if means that it works both directions. So this is a way to use this to find lengths, but also this helps you kind of figure out if a triangle is a right triangle. So any triangle that has a squared plus b squared equals c squared, then you know it has to be a right triangle that way kind of as well. Okay. Yeah, so even if you're younger, you may have heard this, but I want to just kind of review these things pretty quickly as well. So, right, angles, a little bit of review here as well. And I want to do the proof really quickly for a triangle, right? So in a triangle here, right, we have our 3 kind of angles. And we want to show that those angles add up to 180 degrees. So there's a nice kind of trick for doing this. We draw a parallel line. So we draw this parallel line at top. And I don't want to do all of the details here, but then we can kind of see these things one by one. This angle is equal to this angle, right? Then of course any angle is equal to itself. We have the angle here by itself, and then kind of we rearrange this last angle there to form a straight line. So that's kind of how this kind of works there for this one, right? So, right, angles in a triangle can be rearranged to a straight line. So add to 180 degrees. So with that in mind then, anybody kind of know how we do this, how we come up with this for higher polygons as well? So what happens if we have like a 4-sided shape, or a 5-sided shape, or a 6-sided shape, 8-sided shape, different things like that as well, right? So how does that kind of work there, right? All of these all just kind of come from breaking it down in triangles, right? So for example, right, a hexagon, right, with 6 sides can be broken into 4 triangles, right? So that's how this kind of idea works, and really once you know it for a triangle, you know it for any other shape you kind of want as well. A polygon is just what we call a shape with multiple sides. So that's kind of how we could do that as well, right? So if we have any 6-sided shape, right, as long as it's not like too weird of a shape there, and let me just make sure my points intersect here, right? You can just break this shape up into its smaller pieces and go from there. So I can divide this into 4 triangles. And so then each of those add up to 180 degrees. And so that gives us our kind of formula in total. So these are some kind of pretty important ideas, right? I know a lot of you guys know them, but they're good to just kind of review quickly and stuff like that as well. Yeah, so convex, right? This doesn't work for kind of weird-sided shapes, right? So what is an example of not convex? Let me just draw one of those here. Pretty much if you draw a shape, like a normal shape, you're not going to end up drawing something that's not convex. So, right, an example like this is a not convex shape. Okay, so this kind of is what we have in terms of angles in polygons. Okay, so let's then start jumping into a couple of problems applying some of this stuff. Now, remember here, let's try to, once we're solving problems, I want to kind of make sure that we're focused here. Remember, all of these problems right here are examples from old ZIML problems. So hopefully you guys get a chance to kind of check that out as well. And then, right, the rest of the day, we have about 30 minutes left here. We're going to be able to kind of just solve some of these problems together as well. Okay. So now we have our first question. So yeah, let's try, right, focus on solving these problems now. Okay. So we have a regular pentagon, right? And we're kind of going from there. So regular pentagon, B, C, D, E, F, G, right? We have a square, we have a hexagon, kind of things like this as well. So here are the shapes, and we're putting them together like this here, right? So here we have our square drawn, and then sharing aside we have the pentagon. Then putting those together, we have the hexagon. So remember, regular means all the sides and angles are equal. Right? So when we're kind of working with this then here, right, what are the angles that we have in this case? Guys, so let's focus here, please. So, right, what are the angles of a rectangle? Or sorry, square, right? Square, they're all equal to 90, right? For a kind of pentagon, they are all 108, and a hexagon, they are all 120, right? So where do those all examples kind of come from there? Remember, we just figured out what they all add up to, and so then you could divide to figure out what each angle is as well. So for example, this 108 in a pentagon, we have 3 triangles, so we multiply by 3, sorry, not 108, 180. So we can kind of move those around there. We have 180 times 3 divided by the number of sides is 5. Okay, so yeah, some people are kind of starting to be good at sharing the answer. Let's kind of quickly do some of the calculations here together then, right? So we know here that these two angles, ABC and GBC, are 90 and 108. So kind of a good place to start here is that angle ABG is 360 minus 90 minus 108. So that angle there, right, we can calculate right away as 162. So that kind of is our starting point for this problem. I guess I'm going to probably need slightly smaller text in this case. So, right, that is our first angle here. And then we can kind of continue in that way. We then have an isosceles triangle, so we have two 9-degree angles. So angles BAG and BGA are both 9, right? And so then these are kind of where we're getting started from there. Now we have a 120-degree angle here. We have then a 9-degree angle there. And then this is a 90-degree angle. And all of those have to add up to 360. And so then that gives us kind of our approach for the final answer here, right? So let me try to remove some ones here. And so then, right, what we're going to get here then is, right, so finding angle DAK, we do 360 minus 90 minus 9 minus 120. And so this is equal to 141 there. So that's kind of good. Thank you a lot of people for sharing that answer in chat as well. That's kind of the strategy and the kind of answer we have at the end in this case. Okay, so that is practicing a little bit with these angles, right? So if you want to review some of those, right, square, pentagon, hexagon, a lot of those are kind of worth knowing and kind of stuff like this here. And afterwards, right, you can practice those as well. Okay, now let's do a practice problem with the Pythagorean theorem. So what do we have then here? So we have some different information, a square with area 49. And so as we're reading this, a lot of the times you might want to just quickly come up with facts, right? So since the area is 49, all the sides are 7, right? So we have immediately then all the sides of our triangle are 7, right? So 7, 7, 7, 7. And then we can kind of start working from there as well, right? So as you're kind of reading, you can start filling in those angles and stuff there. Okay, so keep reading, right? We have this quadrilateral. We know that AE is 4. So that is our next piece of information there. EF is 5, and FG is square root of 34. So that actually allows us to pretty quickly kind of go through and start putting some stuff in. So we have 4 here, we have 5. 4 plus 3 is 7. So this is 3. And then, right, this side has to be 4. This is definitely one of these right triangles that is worth memorizing, right? So 3, 4, 5 is a right triangle worth memorizing. Okay, so that's kind of pretty helpful here as well. And so then, if we just kind of continue from there, right, we have more sides and more information, we can start filling it. We again have a 3. Since this is square root of 34, right, we can do, right, 3 squared plus CG squared equals 34. So CG must be 5. Yep. So this is how kind of a lot of kind of people, I think, are coming up with the answer, right? We're just kind of working piece by piece along the way. So we have 5, 2, and then we kind of have our final answer from there, right? So AG squared at the end is 2 squared plus 7 squared equals 53. So just kind of remember then what our kind of final answer is going to be there too. So remember kind of when we're doing these things, right? We always kind of want to kind of work those piece by piece there. Okay, yeah, so we want 53, right? Remember, it's AG squared as what the final answer is in this case. So the Pythagorean theorem, right, directly tells us AG squared in that case, right? So we actually just have a final answer of 53 here. Okay, so really quickly, since somebody asked, right, Areteem, we do some kind of supplemental online math classes, right? We just want to try to expose people to kind of more different math they might not see in school. We do a lot of math competition prep, different things like that as well. Right, so this problem is really just kind of a practice with the kind of Pythagorean theorem in this case. So we're just kind of putting a lot of those kind of things together there. Okay. So next question here, right? Let's do kind of 2 here now that are dealing a little bit more with some area stuff. We want to start moving into a couple different kind of questions and some things we can be talking about with area as well. So I want to skip ahead a little bit, then I'm going to kind of go back a second to do one more of these problems here. Let's do this question first. Okay. Guys, let's please focus on some of these problems here. So we have squares with side lengths 4 and 6. So we have a bunch of 4s here. And we have some 6s around here. And then we can kind of go from here. So off-topic things should not be talked about here. Okay, guys, so please only talking about just the problem and kind of relevant stuff to the problem here, please. So, right, we have these squares and stuff like that in this case. Now, we could use similar triangles and stuff like that to try to find the area of this triangle directly, right? So we have this kind of shaded region. The base is 10. We could find the height, stuff like that. That would kind of work as well. So, right, do we have to do that here? Actually, right, remember, especially for areas, you want to think about some ways to kind of trick your brain to doing it an easier way as well. So can we find the area of the green triangle? Yes, right? It has a base and height of 6, right? So where does this height of 6 come from? Well, remember, if it's in a square, this is a right angle. If we draw the height in, the height can be sideways. That's perfectly fine, right? And so that has a height of 6 as well, right? So that's kind of just going to be 18 there, right? So 6 times 6 divided by 2 equals 18. Now, why is this helpful, right? This is kind of the real trick here. Can we find the area combined? Do we know the area of the orange plus green together? Well, sure, right? This is just 10 times 6 divided by 2 is 30, right? Because that is just, right, the base and the height. We know kind of then together the side on the left is 6, the top together is 10, so that is 30 there. So putting it all together, we have kind of a nice finishing step to the problem, right? Then, right, orange equals, right, total minus the green. So we just have to subtract from there. So our shaded triangle is 30 minus 18 is 12. So that's kind of a nice way of kind of going about solving kind of the question from here, right? You can do some other tricks and other things like this kind of there, right? So let's try to slow down chat a little bit more as well. All right, so 25 seconds now here. So yes, our answer is 12. All right, so let's be kind of a little careful and a little bit kind of mindful of the messages we're kind of thinking about here. So yeah, you can do the total and then subtract off what we don't want and get 12 in this case. So I'm not quite sure how people are getting 10 in this case. We should have kind of an answer of 12 right here. So we need to be a little bit careful. 12 should be okay here too. Okay. So in terms of similar triangles, let's do kind of a problem next involving some similar triangles here. So yeah, so I'm not quite sure how people are getting 10. If somebody wants to explain the kind of 10 there, you can let me know, but it's not going to be quite 10 in this case. 12 is the correct answer for that problem. But now let's kind of look at this problem here. So we have a right triangle with a angle of 90 degrees, of course. We know here then the length AB is 4. So we have a side of length 4 here. And we know that BC is 5. D is the midpoint. Remember, midpoint breaks it down into 2 equal pieces. So we have 2 and 2 there. And so that DEF is a right triangle with that kind of angle there as well. Okay, so remember, and this is a really perfect problem of similar triangles, right? So remember, similar triangles are triangles with the same angles, so their sides have a common ratio. And this kind of is a pretty standard kind of type of problem that is going to use these kind of similar triangles over and over and over. Okay, so what kind of similar triangles do we have to begin with? So a good starting point here is to look at triangle ADE, right? So when we have something kind of here, right, what can we kind of say about this situation in terms of the kind of DEF there as well? So everybody kind of okay that we're just kind of shrinking this down, and that's kind of how we're going to be getting this kind of angle in this case here to start, right? So we're kind of looking here at how we can kind of shrink our triangles and start going from there. So this kind of is a good place to start on this problem here. So, right, what happens here then is, right, since D and E are the midpoints, all the sides of triangle ADE are half of ABC. So right off the bat then, we can start kind of cutting these things in half there. So we know that we have a 2, and then we have a 2.5, or let me write that as 5 halves in that case. So in particular here, DE is equal to 5 halves right there. Okay. That's exactly right in this case. Now, we also know that the two triangles, the big triangle and our shaded triangle, are similar, right? So also, triangles, right, ABC and DEF are similar, right? So this kind of tells us here in terms of ratios then, right? AB to DE is the same ratio as, right, then BC to EF. And so this is the most important piece of information right now. So once we have this piece of information, we're good to kind of start finding information. So we know AB is 4. 4 is to 5 halves, as BC, which is 5, is to what? So this kind of is our missing information here, right? So here's where now we have our kind of similar triangles, and we can kind of find our ratio in that case. So when you kind of do this and find this missing ratio here, maybe let's not talk about this too much. This is going to be 25 over 8. I guess actually this is kind of pretty easy to kind of do there, right? So yeah, 25 equals 8 EF, and then we have this right there. So how do you get this, right? This is times 5/8. So 4 times 5/8 is 5 halves. So 5 times 5/8 is there. Now, why are we done basically at this point, right? Let me kind of erase this so I can work on the side here. Well, for finding the area, right, the area is equal to 1/2, right, base times height divided by 2. And now we have all of our information. The base is 5/2. The height is 25/8. And then we divide by 2. So this is 125 over 8 times 4, which is 32. So that's kind of good that way as well. Okay, so yeah, final answer, this area is equal to 125 over 32 in this case. Okay, so let's not worry about square root 2's and things like that right now, right? Remember, things like pi is a number, square root 2 is a number. You could have an approximation for that number, but right, in a lot of ways you can just say square root 2 is square root 2, right? That's kind of stuff that you can just kind of keep in mind as well. Okay. So, next question here, I really kind of like this question because this is another good kind of idea that you want to think about here. So, we have a square ABCD and point P is on the diagonal AC so that this ratio is 1 to 3 right there. And we know that AB is 10. We want to know the area of a BPC. Sorry there. Okay. So 10 and 10. What can we very easily calculate? We can very, very easily calculate ABC. Right? So everyone should have no kind of troubles here saying, right, the area, right, area of triangle ABC is 10 times 10 divided by 2 is 50 in this case. So, right, for a lot of these problems, even if you don't know where to start, you should start with what you can do, right? This is just base times height there divided by 2. We have it in that case. Now, what do we know about the pink triangle I'm going to draw here, and this kind of, let me draw it in red, right? Or no, not red, blue, right? These two triangles put together, right? So we don't know anything about them separately, right? But put together, we have that 50 equals the pink area plus the blue area, right? These two things add up to 50 combined in this case. Now, here is the very important fact. Yeah, so 37.5 Okay, so yeah, even if you have the answer, let's kind of see where it comes from, right? So if you wanted to find the base and the height of these kind of triangles, one way to do it would be tilt your head sideways, right? So let's think of these triangles having a base of AP and PC, right? So if we use PC and AB, right? So both of these triangles, right, have the same height in that case, right? They share this height that I just drew in there, right there, right? This height is the one right there. So what does that tell us if you only change the base, right? I like thinking about this, stretching stuff out, shrinking stuff, right? Stuff like that as well, right? We know then that the ratio of those areas is 1 to 3, right? So since they share the same height, the kind of blue area is divided by the pink area is 3, right? It's 3 divided by 1. This kind of ratio there is 3 to 1 in this case. Okay guys, let's try to focus and kind of worry about this here. So what does this tell us then? 1/4 of this is 12.5, right? And then we have to multiply by 3. So let me just write both of them down, but remember which one is our answer, right? So pink area is then 50 divided by 4 is 12.5, and the blue area, the answer is 12.5 times 3 is 37.5. Yeah, and so really here, I want you to think about these kind of ratios and stuff like that. That can really help you out in kind of thinking about triangles a lot of times as well. Okay, guys, let's not be mentioning other people, right? Let's all just try to get along and stuff like that as well. Okay. So let's look at 2 more questions, hopefully, in the next couple of minutes. Then maybe I'll leave you with a challenge question for the end. So here we have 3 circular arcs with centers on an equilateral triangle of side length 4, right? So remember here that equilateral triangle means all the side lengths are the same. Well, if all the side lengths are the same, right, and they're all 4, we have a bunch of 2's that we can kind of draw here. So we can break this down into kind of things like this as well. So what are all the angles then in an equilateral triangle? All the angles in an equilateral triangle. All of these angles are 60. Right? So what is important here about the 60, right? Remember here what a full circle is as well, right? That's kind of the importance here. So we have 60, and we have 60 here. So, right, 60 is 1/5, or sorry, 1/6, right? 60 divided by 360 is 1/6. So, right, we have, right, 1/6 of a circle, 1/6 of a circle, and 5/6 of a circle, right? So this kind of is our key observation and kind of the key thing we want to be thinking about in terms of the problem, right? So if that kind of makes sense to you, then you're kind of in good shape, right? So we have kind of 1/6 of a circle, 1/6, 5/6. So what is our kind of total here? We have then, of course, 7/6 of a circle. So in total here, 7/6 of a circle. And what do we know about that circle? The circle has a radius of 2, right? So this gives us an answer for the area then. How do we find the area? Well, it's a fraction, right, of the circle. So we could look at that kind of fraction as well. So this area here is, right, 7/6 of the circle. Well, the circle has an area of pi r squared, so pi 2 squared. So this is 6 pi, right? And we're kind of doing this calculation there as well, right? So we have 14 over 3 pi. And so that is going to be our answer, right? So kind of that is kind of how we're going to have this, right? K equals 14 over 3, or 4 and, right, 2/3. Both of those answers are correct as long as you have the space between the 4 and the 2 there, right? Because those are kind of definitely different kind of things there as well. Yeah, so we're almost to the end here. So we're not gonna, I guess I can turn slow mode off after we're kind of wrap up and everything here. So I want to give a hint for one last problem. And this is a good fact to do as well. So hint slash fact, right? What is the area of an equilateral triangle with side length s? This is a fact that you could prove, right? I'm not going to talk about it too much right now, but this is a very, very kind of useful fact that you should know. So what if you have an equilateral triangle and you know all the sides of that kind of triangle are s? So we have 3 sides of that triangle, s, s, s. Does anybody know a formula for the area of this kind of triangle? This kind of is pretty useful in a lot of cases. So this one's kind of good to know. Yeah, so it's s squared times square root of 3 divided by 4. So that's kind of very, very helpful for something like this. You can use Heron's formula to prove it, or you can use just a 30, 60, 90 triangle to prove it, things like that there. The easiest way to prove it is you can actually just draw the height, right? So you can draw this height down here and then start looking at the triangles that you get kind of that way as well. So that's kind of useful there as well. So this problem I want to leave kind of as a challenge, right? So this problem is a challenge here, right? So problem you will need this equilateral triangle formula, right? So this involves, right, the area of circles as well as equilateral triangles. So you're going to need to do kind of multiple pieces of this together. So do you guys want the answer so you can check your kind of work later on? It's a little bit harder, I think, than you probably might initially think here. It's not going to be a nice answer in this case. So let me just give you the answer. So the answer is 24 pi minus 18 square root of 3. So this one is a challenge question. So this one is not kind of easy to necessarily do. I'll let you guys kind of think about that a little bit to try to kind of come up with the answer there. So yeah, not the prettiest of answers, but that's what it is. So we have to kind of think about it there. Okay, so really quickly as an end here then, right? Remember that a lot of these problems are coming from kind of ZIML. So hopefully, right, everybody has a chance, right? Try visiting this place, right? We have free daily problems there. We have kind of monthly contests. Keep your eye out for some videos describing some maybe monthly contest information and stuff like that we will do starting later this week. And then otherwise, hopefully, I'll see you guys all again in the future. I will leave here slow mode off a second for the end, and I will see everybody a little bit later on as well. So we probably, as of now, we might post a video tomorrow. We're going to kind of see different kind of options moving forward and stuff. So if you enjoyed this, right, please let us know, right? So yeah, let us know if there's kind of still interest in some of these, right? Let us know. Off school, right? We're still kind of figuring out exactly our plans for the next couple of weeks and stuff like that. But everybody stay safe, wash your hands, right? Don't cough on people, right? Let's try to hopefully let people kind of be healthy, and then our kind of world will go back to normal, hopefully sooner, better, rather than later. So I will see you guys later on then. Goodbye.